Hello there, 8th graders. This is Mrs. Minowitz, and I'm here to talk to you about the relative age of rocks. So I am out at a meeting today, so instead of having you do something else, I thought you'd just love to listen to my voice and hear us talk all about rocks. So we're going to start today talking about the relative age of rocks. And what relative means is just that how is the age relative to something else? So how is the age compared to something else? We're not necessarily going to go into a lot of numbers because we're really just looking at how do we figure out which rock is older than the other. So the first thing I want you to think about is how old or what the age of the Earth is. So scientists believe the Earth is blank years old. What do you think? Come up with a guess. Your best guess. The best estimate for how old the Earth is about 4.5 to 4.6 billion years old. Okay, between 4.5 and 4.6, depending on where you look, you might get something very, or you might get either of those numbers. One of the things I want you to think about is if you were to take 4.6 billion years and you were to kind of condense it into 1 hour to see how long those things took, because 4.6 billion years is really hard to wrap our minds around. We don't think in billions of things. If we were to kind of condense it into 1 hour for comparison, the first modern man doesn't appear until 59 minutes, 59.9 seconds. So compared to the age of the Earth, we are really, really young. Relative age, is just another way of saying the approximate age of rocks. We're not really going to deal too much with numbers, and we're more looking at comparisons between which rock is older than another rock. So to figure this out, there's kind of two rules or laws that we use to figure this out. The first one is called the law of superposition. Okay? And all the law of superposition says is that older rock is beneath, below, or under younger rock. Okay, oldest is going to be on the bottom. If you think about like your laundry basket, wherever you throw your clothes, if you're looking for something from early in the week, you need to go to the bottom versus something from yesterday might be closer to the top. Older rock is going to be beneath younger rock. Okay, so if you look at your diagram here, E would be the oldest layer, and A would be the youngest layer. Right? There is a second rule, or law that is used when we're talking about the relative age of rocks, and that is the law of horizontality. That's kind of a mouthful. But all that means is that that layers of rocks are going to form horizontally. And they're going to stay horizontal unless there's something there to tilt them or to move them. So if you look at the picture shown here, you've kind of got these, you can see these even or horizontal kind of lines or layers showing you how those layers of rock are formed. Now this law says that it's going to stay that way unless there's something to tilt them. So if we look here, we've got this picture taken, and you can clearly see some different horizontal rock layers as you look at it. But there are two things that can tilt rock layers. The first thing that can tilt rock layers is what's called an intrusion. And intrusions are when molten rock, that would be our magma, it squeezes into existing rock and cools. We would get an intrusive igneous rock. So if you look at the diagram, it's usually seen kind of as different layers or moving through those horizontal layers and kind of filling in that area. That's called an intrusion. It might help to think of this like intrusive as far as igneous rocks are concerned. And if you look at this picture here, we can kind of see along the side here some nice rock layers. And then we've got this thing that kind of moved up, igneous right here. That's called an igneous intrusion that's made of magma that cooled. And then there's some erosion. The other thing that can tilt rock layers or move them is what's called a fault. And a fault is just a break in the Earth's crust, and blocks of the crust slide relative to each other. This is often how we get our earthquakes, are pieces of Earth's crust moving. And now we've got our diagram here of a fault. If you look at your diagram on the bottom of your page, okay, I would like for you to pause the video, okay, and once you've listened to the directions, identify on here, okay, the oldest rock layer, the youngest rock layer, the intrusion, and the fault. So go ahead and pause this, see if you can identify those, and then listen for the answers. All right, so hopefully you've identified your different parts on here. What you should have is that the oldest, okay, rock layer is going to be on the bottom. So you would say that this part here, D, is going to be the oldest rock layer, and then A would be the youngest. E is our intrusion. It's going across or cutting across the other layers. So we would label that as our intrusion. Okay. And then F would be our fault, showing that break in the crust. You'll often see it with a line with the arrows on either side in a diagram that tells you that is a fault. Now I've got another diagram that's not on your picture, but I want you to try some more practice with this. See if you can identify some other things here and put it into practice. So what I'd like you to do is on the bottom of your paper, okay, try to go ahead and put these rock layers in order from oldest to youngest. Oldest to youngest. So use the letters and see if you can come up with the correct order. So pause the video, put them in order from oldest to youngest. All right, I hope that you were able to put these in order. So as we know from before, our oldest should be on the bottom, and on the bottom is F. And then we would work our way upwards. We would get E, D, C, B, and A. F being the oldest, A being the youngest. All right. And I've got one more here for you to practice. And this one gets to be a little bit complicated, but that's okay. I just want you to try it, putting the rock layers in order from oldest to youngest. Make sure that you pay attention to the letters C and H and see if you can fit them in there as well. And this is challenging to get them all in the correct order, but I'd like for you to try to do that. Remember, the oldest is going to be on the bottom, the youngest is going to be on the top. So go ahead and put these in order, pause the video. All right, hopefully you've tried putting this together, and don't worry if you're struggling with this some. Tomorrow we're going to go through this and we'll go through any questions that you have. But we should start by putting them in order from oldest to youngest. So we'll start at the bottom here. We've got A is on here. Then we should have, as we move upwards, B, D, E, F, G. Those are our layers. But now we really want to try to figure out when C and H happened. So if you look here, C had to happen before F and G got there, else it would have cut through there, but it had to happen after E. You can't have an intrusion go through something if that rock layer is not there. So we should put letter C in between E and F. Okay. But then we've also got to worry about this letter H here. Okay. It is our fault. And as you can tell, our fault went across A, B, D, E, and it also cut through C. So that means our fault had to happen after letter C was already there. So this would kind of fit in here. The correct order that you should have would be A, B, D, E, then C, then H, then F, then G. And if you got that, good job. If you didn't get that, I hope you understand my explanation for how it came to be. And we'll go through some more examples of this tomorrow. Okay. So if you flip your note sheet over, if you have not already done so, if you're looking on there, the next thing that you need to know are index fossils. Okay. And index fossils are easy to identify because they are a species that existed for a short period of time. So it's something that didn't live really, really long, okay, in terms of geology. That species either became extinct or we had a new species formed, so you wouldn't see this over a long period of time. And these are really helpful because they can date the surrounding rock layer they're found in. If I have a fossil that I know only existed 200 to 180 million years ago, then I know if I find it in a rock that rock has to be between 180 and 200 million years old. Okay, it's kind of helpful for narrowing things down. One example, okay, would be what's called a trilobite fossil. There's an example of one shown here, and a trilobite is a relative of a modern-day horseshoe crab. But this would be an example of an index fossil. It's useful because it only existed for a short period of time. This has all been about relative age, which rock is older than the other. Absolute age is where you get an actual number. Absolute. We know a number for how old something is. So absolute age is the age in years. If we have a number, this is 182 million years old, then that is what's called the absolute age. So it's the age in years of rocks through a process called radioactive decay. And what happens over time is that atoms break down at a certain rate. And by calculating how much of that has broken down, we can figure out the age of something. And one really common thing that we look at is what's called carbon-14. And carbon-14 breaks down at a certain rate, and we can measure that and calculate how old something is. Now, we're not going to do the calculations in class, but I want you to understand that they use this process to come up with a number that gives us the absolute age. In order to do that process, you have to know what a half-life is. So a half-life is the length of time it takes for half of radioactive material to decay. If we know the half-life of a certain radioactive material, and there's radioactive materials in everything, you have radioactive materials in you, and that's fine. There's nothing wrong with that. Sometimes people think radioactive as dangerous, and it can be, depending on the type and how much there is of it. But if we look at how long it takes those things to break down, we can do some calculations based on the half-life. So if you take a look at this graph here, carbon-14 is a very common thing we look at for radioactive decay and how quickly it is broken down. So if we have 0 half-lives, we have one whole remaining. In a half-life, okay, we would have half of it left. In our second half-life, we would lose half of our half, which is 0.25, and then we would keep going on downwards. But you'd never actually get all the way to 0 because you'd keep taking half of something as you move your way down. It's what's called exponential decay, if you've heard of that in math. So I hope you were able to work your way through the video. We will go through questions from this tomorrow. Don't forget that you have your rock cycle quiz tomorrow, so make sure that you've reviewed and studied for that as well. If you have any questions about that, send me an email, and I will respond tonight. I'll make sure that I'm checking my email as well. Thanks for listening in. Hope you have a wonderful day.